So let's move on. You can ask me questions. First question to you: what is causing you the most trouble in Golang? So please join the Mentimeter. There are some questions for you to answer. I will put the instruction slide up so we can go back and you can join. All right, so what causes the most trouble in Golang? Error handling, yes. I struggle with error handling myself. What else? I'm a little bit confused with the generic syntax for generics. They introduced generics into Golang. If I have to use it, I have to look it up. How can I use it? Because I never remember like the syntax for it, right? So what else? What else is causing trouble with Golang? Not much. Golang is kind of yeah, unused variables. Many modern programming languages are that in enforcing that if statements. Yep, Golang is quite simple, and the simplicity makes it sort of a little bit tedious. But there is not much I like to remember. Like I generally remember the syntax. It's quite consistent. Like the types always come late, like second. Func is quite nice. Yeah, I think it's compile time is amazing, actually. Like if you start with Haskell on Rust, you will kind of miss Golang compile times. All right, next one, Haskell. What's causing you the most trouble with Haskell? I know, syntax. So the funny thing is, like, if you learn Haskell and if you learn Rust and Golang and C++, the only sort of syntax that kind of you remember like forever, you don't have to look it up, is Haskell. Because it's like so simple, like the syntax afterwards. I have to look up syntax for C++, like with some anonymous functions. I don't remember, like, is it the bars or is it something else? With Rust, the same. But with Haskell, like syntax is actually the simplest thing. It is like you have to learn it. Yes, you have to learn it. But once you learned it, it is very simple. Yeah, it is confusing, definitely. Monads are hard, yes. How about folds or list comprehensions? Do you like them? I like them. They are quite, yeah, quite nice. All right, so then next one, Rust. What's hard in Rust? For me, it's definitely syntax. Like I never remember like what is the syntax for something. Especially with the annotations for lifetimes. I always have to look it up. Ownership model, yes. Yeah, concurrency is hard, but concurrency is always hard. The type system is quite nice. It's similar to Haskell. Yeah, the syntax is kind of similar to C, C++. So like if you really see C++ kind of mindset, then the syntax is kind of very alike. So you may feel it's sort of simpler, but in fact, it's not that simple because of all the additional things. Yeah, the methods is huge. So Haskell has some utility methods which are usually reusable across all different collections and different data types, but in Rust you sort of need to memorize all of this. Not yeah, you don't have to memorize. You can look up in the docs. All right. So why do we study those three languages? Or four, or five? Different paradigms? Yes. They provide a variety of paradigms and variety, for example, for memory management. Some of those languages are safe because the memory is managed for you. Some of those languages are safe because they have this ownership model. And some of those languages are kind of unsafe in terms of memory management. Some of them have a very strong type and rich type system. Some don't. All of them are strictly typed, and all of them are compiled, and all of them are very popular and fundamental in a sense of relying on the underlying infrastructure. And they cover the whole spectrum. So if you know those languages, there is no single language that will surprise you with features that you don't know about. You will know about all the features that exist. So all programming languages kind of boil down to those languages in a sense that they will not surprise you with anything unusual. All right, so what is Rust? So Rust has been heavily inspired by Haskell. It's sort of almost like Haskell people thought, yeah, we would like to have a high performance, zero abstraction, manually managed memory language, which has all the nice features from Haskell. And that's how it feels. So it feels that it has kind of has been influenced by Haskell heavily. And if you understood how Haskell handles errors, for example, with maybe and either, then you will feel at home with Rust. It is different way programming than C++, even though the syntax is kind of similar, but the mental model is much more close to Haskell than to C++. It's excellent for embedded systems, for mobile programming and cross-platform programming and for system programming. It's kind of excellent for resource-bound systems because it has a very small runtime. It's very, very tiny language. Also for real-time systems. And because it has this very small runtime, you can use it on IoT devices or everywhere where, memory is kind of issue. So what is systems programming? What do you think? Programming operating systems, yeah? What else? Drivers, yeah. Have you used any database? What databases you know? MySQL, MariaDB, InfluxDB. Who wrote those? Who wrote databases? System programmers, right? You're using Docker? Who wrote Docker? System programmers. You're using any Python with machine learning modules? Who wrote those? Who wrote those modules for the machine learning people to use? System programmers, right? So system programming is not just OS. It's like everything everybody else is using, right? Yeah, Kubernetes, exactly. Who wrote Kubernetes? System programmers. Who wrote VirtualBox? System programmers. There is like gazillion of tools everybody is using and takes for granted, but somebody needs to write that, right? So it's all system programming. So Rust shines in system programming, right? So if you need to do something like this, Rust is kind of a good tool for the job. Is it necessary good tool for a job when you're writing applications? Not necessarily. Maybe other languages are better for writing applications, right? So application development is kind of a higher in the stack. You sort of usually interfacing the end users. System programming usually interfaces with other developers. It's kind of deeper in the stack, right? So the end users don't directly talk to, Kubernetes, but they are using Kubernetes eventually, right? All right, so about Rust, statically typed, no garbage collector. What garbage collected languages do we know already? Golang, Java, what else? Haskell. All right, compile time memory management. Um, that's quite a unique feature actually. Um, so is C compile time memory management or not? No. It's runtime memory management. Like you have to deallocate stuff yourself, right? And it happens on the runtime. The compiler is not like telling you, oh yeah, here you will have a memory leak, right? You will have a memory leak at runtime, but not at compile time. So Rust is also quite a unique language. It's like the only language which actually has a compile time memory management. You either have C, C++, which don't have memory management and all, everything is done manually, or you have a garbage collected languages like Java, C Sharp, Python, Haskell, and they have a garbage collector and memory is managed for you. You not manage this memory manually. And then you have those two worlds, and Rust is kind of in the middle because you are managing memory, but at compile time, right? Um, that's why the ownership model, and that's why this borrow checker is so annoying because the compiler always gets in your way, right? But that's where the memory management happens at compile time. But it has manual memory management. Manual in a sense that the programmer isn't in charge of like what to do with the memory. Full control, right? You don't have that with other languages. Like you don't have that with Haskell or with Python or with Golang. You have a little bit control with Golang, but not a lot. You have a little bit control with Haskell, but not a lot. And then here you have full control. You can do everything you need. And surprisingly, there is no inheritance, right? It's a modern language, and OO is present because you have methods to your structs, but they dropped inheritance completely, right? What are the modern languages that dropped inheritance? Golang, right? It's another example where you have methods for your structs. You have sort of like an object model where you can do object-oriented programming, but there is no inheritance. So one reason why it is dropped is because inheritance turned out to be a kind of a pain in the ass in maintenance and in like programming in general, right? It felt like a good idea at the time, and many languages still use it. You have it in Java, C Sharp, C++, and so on. But in terms of like the costs and benefits, the costs outweigh the benefits. So like it's better not to have it. um, so what do we do instead? Like if let's say you have a person type and you have a manager and manager is a person and you don't have inheritance, how we model this, how we usually do this. We do this by delegation. So we say, I have an instance of a manager, and then I have a person to which I delegate all the person stuff, right? So instead of inheritance, we do by delegation. And mutability. So one pain in Haskell is that like everything is immutable, like by default, and there is no like mutability, right? So every time you have some sort of variable like thing, you have a value, you cannot mutate it, like it's there and that's it, like forever, right? So immutability in Haskell is kind of pain in the ass a little bit. But it's a kind of a strong point of Haskell too, because it ensures a lot of guarantees. Here, they said, okay, immutability is great. Like we should use it everywhere where we can, but it's sometimes pain in the ass. So we have to have a mutable state as well, and you can have it on request, right? So if you mark something as mutable, it's the same as in Golang or C++, but by default, they encourage you to think about it and try to have as much immutable things in your code as possible, right? So mutability on request only. The field is, as I said, like you're using semicolons, you're using colon for defining the type and the curly braces. So the field is sort of C++-ish or Java or, C#-ish, but it's a little bit different. So types usually go at the back, similar to Golang, not in the front. That's another feature of modern programming languages, that this notion of type being in front and then the variables being later is also kind of not consistent. So modern languages are trying to sort of organize it in a more consistent way, and usually we're doing it this way. Haskell is it doing this way, Golang and Rust are doing it this way. So then when you go back to C and C++, you have to sort of revert that a little bit. It's similar. And then you have this kind of a rich macro system. We will not dive into macro system of Rust ourselves in this course. If you stay and do masters with us, we will be working with Rust macro system later in the master program, but not in the bachelor level. You may kind of use it for some of the simple things, and you may use it for your bachelor thesis, but we don't have enough kind of time to dive deeply into that, but it's very powerful. You can do quite powerful things with the Rust macro system. All right, so here are some resources. So before I do the resources, so because of the very tiny runtime system, Rust heavily relies on additional libraries to do a lot of stuff, right? So unlike Golang, where you almost everything you need you can do without external dependencies. In Rust, almost nothing can be done without external dependencies. You almost always have to work with some other people libraries, right? So in Golang, they have a philosophy where all the crypto, all the web, HTTP, JSON, everything is part of the standard library, and it's defined on the language level, and then you have it kind of defined without additional dependencies. You can sort of code a lot of networking things without relying on external libraries. And you should, because it eases off the maintenance. In Rust, they went for the very tiny core, very tiny runtime system, but almost everything you need, you have to get from outside. And those packages are called crates, and there is like a big repository of crates, and they have a variety of quality. So some are really bad, some are quite okay, but you have to rely on it. So it is a little bit similar to JavaScript and NPM, right? To manage all this complexity. It's a little bit similar to Haskell. Haskell also has sort of like a middle ground. Some functionality has to be imported from outside projects, but Rust heavily relies on that, on the crates. All right, so then just grade according to your own feel, which languages feel easier than others. So you can kind of put the sliders and like rate relative to other languages, like what you feel the relative difficulties of those languages. Yeah, why Rust is not here? Rust should be here. So these two, like C and C++, it's surprising that you're kind of thinking C is harder than C++. Objectively speaking, C++ is a superset. So if there is anything hard with C, it's also in C++, but C++ adds extra hardness. Yeah, Python is kind of the easiest, relatively speaking, here. And Haskell is, yeah, quite hard. So I did that exercise as well. And this is my opinionated list. And I think Rust is kind of close to Haskell, but it's a little bit lighter. It's a little bit easier. I also think Haskell is the hardest language I've learned. But I think Go and C are quite similar. I don't think C is inherently hard. And then C++ it's harder than those two. That's what I think. So it's a little bit similar to what you said, but a little bit different here. I also think Golang is kind of similar to C. Like once you know C, Golang is easy. But C++, no, C++ is definitely not that easy. It has some easy parts, but it also has quite a lot of hard parts. All right, so Rust, yeah, so the point of this was that Rust is sort of on the hard side of the spectrum, right? So Haskell and Rust might be two most difficult languages that you will ever learn. All right, so then if we go into Rust, we do have to understand heap versus stack. And I hope you have some intuitions and you kind of understand it because of C and C++. You definitely don't understand it because of Golang. But what is heap? So heap is all the memory that we allocate ourselves and we don't know how much we need. So we have to allocate it later. So we allocate it during runtime, right? So heap is all this memory that the allocators allocate for us, right? So every time you have new, or every time you say malloc, or every time you sort of allocate something with the pointer, then it's a heap, right? So it has two characteristics that if you need something big, usually you have to use heap. And then that if you are using the heap memory, then it's kind of slower than the stack memory, right? So what is a stack memory? Stack memory is the one which is allocated for you when you compile your program, and the program knows how much memory you will need for executing a given function. So it allocates that amount for you, and then you can sort of use it. It has a known size because the compiler can work out how much space you need to do the computation. It follows the last in, first out model. So it's like a stack. So you're adding things on top and picking things from the top, right? So like if the stack is empty and the first thing you put on and you put something on top, you cannot get this thing. You have to get this one first and then get this one, right? So it's like a stack, like a data structure. It has a very fast access. And then usually stack variables get released the moment they go out of scope. So our stack is kind of freed the moment your function finishes or the variables go out of scope, right? So you remember this from C, I hope. But if you don't, another quick comparison, if you allocating your variables inside the function and you're passing by value, then you're most likely doing stack things. If you're passing something by reference, or if you need something to work across functions, you need heap memory, right? Why I'm talking about this? Because it becomes important, right? In Golang, it's not important. In Haskell, it's not important. In Python, it's not important. In Rust, it's important. And in C, C++, it's important. So every time you're analyzing a C++, C, or Rust code, you have to know if this is on heap or this is on stack. Like there is no way that you don't know. You have to know, right? So that's an additional workload, mental workload that the system programmers have to carry. That's why, as I said, when you're developing an application and you sort of don't really care so much about the performance or about the memory allocations, you say, yeah, let the runtime system deal with that. Then you can choose languages which are kind of helping you, right? So Kotlin, if you're doing a mobile development, will do that for you, right? But if you're programming something and you really have to squeeze the most performance out of the system, you will do this, and you will have to know what is what. All right, so here we have a small snippet from Golang. We have a struct, a student struct with a name and age, very simple thing. And then we have two functions. So let's look at the first function, right? So the first function takes a name and the age and creates an instance of a student. So where is this student instance allocated? Is it allocated on the heap or is it allocated on the stack? Yep. It's allocated on the stack, exactly. And then when I say return student, what happens? What happens in that line of code? A copy is created of that stack allocated student, and that copy is on the heap, and that copy is returned to the caller, so the caller will have access to it, and the local stack allocated student is destroyed, right? So we have now two students. We have the original one on the stack, and at this bracket, the local one is destroyed, and the heap allocated one is passed to the caller, right? It works exactly the same way in Golang as it works in C and C++. Make sense? Makes sense. All right. So then we have a second version, which is exactly the same. It does exactly the same thing here, and then it passes a pointer to that stack allocated student to the caller. Okay. So what will happen in C++ or in C if I do this? What will happen when I do code like this in C++ or C? I will have a core dump. My program will panic because my caller will try to access student, and student with this bracket will be deallocated. So it will try to access a memory location, which is invalid, right? Because the stack memory, which was passed for this function at this bracket here has been freed. So this student, this local student, does not exist anymore. It is gone, right? But somebody has a pointer to it. And then when they try to access it, you will have a crash. Your system will fail, right? What will happen in Golang? Will the program crash if I do this in Golang? No, it will work, right? Why it will work? Because Golang works out, the Golang compiler and the runtime system, they analyze what you did and they say, oh yeah, we have this stack allocated student, but we need to pass it to the caller. So we will have to make a copy but on the heap such that this pointer does not point to the empty thing. So then this allocation is actually not done on the stack. This allocation is done on the heap. And then this return returns the pointer to the heap allocated student. And then this code works in Golang. And in Golang, you only have one copy. It's heap allocated student, right? The code looks exactly the same. I'm doing line 9 to 12 is exactly the same as 18 to 21, but this one is stack allocated and pass by copy. This one is heap allocated and pass without a copy, right? Strange, but that's how Golang works, right? But you kind of need to know that the Golang helps you not to make memory errors or memory bugs by doing code like this, because in C that would be a bug, and in C++ that would be a bug, which would lead to a panic, to a core dump, like the program will crash. So this is kind of important to understand. All those variables normally are on the stack, and we pass them by value, right? How is the name and how is age passed to this function? By value, right? How is the student returned here? By reference to a heap allocated student. And how is the student returned here? By copy of the stack allocated student, right? So this is passed by value. This is passed by pointer, by reference. All right, so Golang manages the stack and heap allocations for you. You cannot tell Golang, no, I want it on the heap or I want it on the stack. Golang will kind of do whatever the Golang thinks is the most appropriate, right? You thought you're allocating something on the stack and passing a pointer to an invalid memory. Turns out that's not the case, right? In C that would be the case, but not in Golang. And then you have some memory guarantees because of that. So Golang kind of takes care not to have certain memory bugs that C would have, but it takes some of the power of your hands, right? With C, you have the power to do those bugs. In Golang, you don't, right? And then normally in memory managed languages, like the ones with garbage collector, you don't have that power because the system will prevent you doing something stupid. So in Rust, it's the borrow checker, which prevents you doing those bugs, and the borrow checker enforces it at the compile time. All right, so let's have a quick look at the types. How are we doing with time? Yeah, fine. So we have normal value types like, numbers, booleans, strings, and things like that. Constants like str is the value type. We have tuples, structs, arrays, slices, and enum types. Enum types are quite interesting. They are not like enums in other programming languages, but all the other ones are kind of very similar. So all the other ones are kind of known from C family of languages, and enum will feel familiar because of Haskell. Enum is sort of like a algebraic data type. So you can define your algebraic data type using enums in Rust. So we have a simple type alias, exactly same as in Haskell. And then we have some basic types like integers, unsigned integers, and you specify how big they are. So you go from 8 bits to 128. Same for unsigned. You have two types of floating point numbers, bool, and then you have strings and you have str. These ones are immutable and these ones are like constants. And this one is a variable length, kind of a string like in other programming languages. There is a little bit to understand between these two and where to use one or the other, but you kind of get to know it with practice. It has exactly the same tuples system as in Haskell. So if you've used tuples in Haskell, it's kind of exactly the same. And you have an empty tuple, like a unit tuple, which is an empty. And then you have structs, and structs are quite powerful in Rust. They go beyond what you can do with C or in Golang. And like the best way is to sort of look at some examples. So you have structs which define named fields of the struct. You can have an empty struct, and then you can have kind of like a struct, but without names for your fields. So that is sort of like a tuple, but tuples are not named. So like the normal tuple is something that is anonymous, like it does not have a name. So a tuple between like str and e32 is a type which is kind of the same as every other type which takes the i32 and str here, right? But if you want to distinguish, like if you, for example, say I have age and name, and I have runtime and machine, and you want to distinguish those tuples, you will use a struct, which is the tuple struct. So you'll use like human age and the machine runtime, and the fields will be the same, but the type will be different, right? And then you can simulate this with the struct that has those indexes instead of names, and it's exactly the same like this. So those two are kind of identical. It's like a syntactic sugar, like which one is which. And then you have the normal, like the one like here. Yeah, I don't know why this one is here. This one is not related to structs. Okay, syntax same as in other languages, and the same as in Golang, you can have IMPL section, which defines methods on your struct type, right? Remember, you have a struct in Golang, and then you have your funcs, which take the like the first part is the reference or the value of a particular struct, and then you define some functionality. So it's the same here, but you have it in like a block. So it sort of feels a little bit like doing a class in C++, but it's a little bit different and you don't have inheritance, right? All right, and the developer controls the memory alignments of structs. Ooh, what's that? So here is the simple struct with a value, and then this IMPL implementation for the value for this type. And then you specify your functions inside the curly braces, inside the block, right? And then you instantiate them by either passing the name or passing the parameters for the value. It's kind of very similar in feel to Haskell. It kind of feels the same way. So what is the memory alignment and why do we care? So those are the topics which come with Rust because we are now changing from like an application developer, which was using Golang or Haskell or Python or, Java or Kotlin, to somebody who is using like system level programming and system development. And we really care about memory and we care about allocations and things like that. So then what is memory management and why do we care? Yes, we care because of the performance. We care about the control. So what is? Memory alignment is how your variables start and how they sit in memory, right? So memory is like a continuous block of RAM. It's not kind of, I will wave my hands, right? So if you imagine, like we have this space and it's our memory. It has addresses, right? So there is an address for that slot. There is an address for that slot. How big are the slots? Yeah, so it depends on the architecture. On most modern 64-bit CPUs, those slots are 64 bits, right? So 8 bytes. It's like this slot. So this slot has an address and this slot has an address. But in between, you don't have an address, right? So the alignment is how your data structure kind of starts because it has to be addressable. You have to say, I want this bool, or I want this name, or I want this int, right? So it has to start at the boundary of the words. Those, let's call them words. And then we have addresses. So then if something is smaller than the word, then you will have a padding, right? So if I'm using I8 and I'm using only the first byte, I have 7 bytes which are unused, right? Because the next thing has to start at the boundary of the word, right? Otherwise, it would not be addressable. Otherwise, I cannot say, give me that variable, because like in between, there is no address. The addresses always start at the one kind of the boundary layer, right? So it's in 64 architectures, you can sort of think it's almost always 8 bytes, right? 8 bytes I'm dealing with. And then different data types have different requirements. And then you want to be using those boundaries kind of in an efficient and effective way, right? So for example, it matters for how you are accessing the data, how the memory is being used, and how you can fit it into the cache such that you don't have cache misses, and also how how much padding you're using, so you're wasting memory, right? The more padding you're using, the more memory you have to use because you're wasting it for the padding. So here we have like 2 examples. We have one struct which starts with unsigned integer. So you have 8 bytes. No, 8 bytes to occupy, but this 8 bits occupy just 1 byte. So then you have 7 bytes of padding, right? Then you have B, which occupies the full word, so 8 and 8 bytes. And then you have U16, which takes 2 bytes, and then have 6 bytes of padding, right? So in total, this struct will occupy 24 bytes, and it will kind of have 13 wasted because it's like used up for padding, right? So then if you do this, if you start with the largest one, and then you do you're doing the second one, and you start with the 16, and then this guy is actually able to fit as the second part of the first one. So we occupied 16, and then we can actually squeeze in the second one here, and then have only 5 bytes of padding. So our total occupancy for the second struct will be 16 bytes. So you see there is a huge benefit, and we only wasting 5 bytes of padding in total, right? So those things, like when you designing your structs, you have to pay attention that you make the memory alignment kind of in your favor. All right, there are arrays, same as in other programming languages. So it's a fixed length, and it's fixed type. So you cannot have multiple types like in most languages. And then you say, I have 10 of I32 in this array. So you specify the size kind of with the colon. And then you can initiate it with the default values. You can initiate it to zeros. And then you can also initiate it to a particular value by doing this kind of size syntactic sugar, right? I never remember all those syntactic sugars, so I kind of need to kind of recall those, but I remember that that I can do it, right? All right, functions, super nice, same as in Golang. Instead of func, you're doing fn. The types go after colon, but it's a little bit inconsistent because the types for your parameters go with the colon, but the type for the return goes with the arrow. It's like, why did you do that? Like, why did you use the colon for the type for the return as well, right? So there are a little bit like annoying, inconsistencies, which make you not remember, like if you haven't used Rust for a while, you have to sort of go back to the syntax, and the syntax is like, as I said, it's kind of annoying sometimes. So then they have closures and they have higher order functions. So like the functions in Rust, they really feel like Haskell, and they have a lot of functional feel when you're doing programming in Haskell, in Rust. It's very similar. All right, we do have some quizzes. So jump in. All right, so let's do it. So closures and anonymous functions are the same thing. So if you've done some Haskell and some Rust, in Rust they call them closures, and in Rust they are kind of confusing because they are not the same thing. So this answer is correct. We go to get to there in a moment. So we have a little bit more to drill into that topic. So anonymous function is a function without a name. Is that true or false? That one is easy. It's true because it's in the name. It's anonymous, so it does not have a name, right? That's exactly what anonymous functions are. Those are functions without a name. So every time you have a lambda, some languages call them lambdas, some languages call them anonymous functions. And also some languages have lambdas and anonymous functions as separate thing, right? So in Java, they sometimes say you have this anonymous function if you have a function without the name, because you can have a function without the name. And then the lambdas are this kind of internal thing, which you also have a function without the name, but using slightly different syntax for it, right? But they are the same thing. It's just syntactic sugar. Conceptually, anonymous functions don't have a name. So then the second question is, closure is a function that captures something from the outer context. Yes, that's exactly what the closure is, right? So if I have a function and I captured something from my outside context inside here, I have a closure, right? So then logically following those two definitions, closure must be anonymous function, true or false? It's false. So closure does not have to be anonymous. You can have a named function which captures something from the outer context, right? But not in all programming languages you can do that, right? So you will have a homework. Yeah, really, really tight competition. All right, so we have. All right, so then in Rust has this limitation, and that's very annoying. In Rust, name functions cannot be closures. That's true. So in Rust, you cannot have a named function which captures something from the outside context, right? We will talk a little bit why. But in other programming languages, you can. Right, we have some reshuffling. So that's the homework. So you should write an example function which is anonymous or named, which captures something from the outside context, right? That's an exam question right here, right? So if you do it at home, you will have one question for exam already done. Right, so let's have a break. Let's have 10 minutes break. Oops. And then after the break, we will have the quiz review because the tutors will come. And after that, we come back to Rust. Sorry, I was muted. So thanks, Rafael, for pointing that out. So I was basically explaining anonymous and named closures and what the closure is when it captures something from outside itself. Okay. What we have here. In Rust, all anonymous functions are closures. So the previous question was, in Rust, all closures have to be anonymous functions. And that was true because you cannot have a named function which is a closure. But can you have anonymous function which is not a closure? Of course you can. All the anonymous functions which don't capture an outside environment are not closures. Which is confusing because they still call them closures, right? Even if they are not closures, right? So this is this sort of a confusing aspect of Rust, that the naming is a little bit misaligned with what it is. Yeah, very tight up there. So why is it so complicated, and why they are so confusing about the terminology that they call all anonymous functions closures, and why they prevent named functions to be closures? Well, it boils down to memory management, right? So because Rust has to manage memory, and because when you're capturing something from outside your function, it's like a very special case you have to deal with about memory management, they treat it like as a special case. And that's why normal functions, which don't capture anything from outside, are considered like easy to manage because they are self-contained. But everything that potentially can capture something from outside has to be managed at compile time, and that creates this sort of overfitting where every anonymous function is analyzed as if it was a closure, but some of them are not, right? But in case it is, Rust needs to know what is it capturing, like what is happening with the memory outside of that function. And that's why it's kind of tricky. All right, another theory question. What are higher order functions? Yep, that's an exam question right here as well. What are higher order functions? Yeah. So functions that hold another function. Yep. So functions that use other functions as argument, or that return function as a return. That's a higher order function, right? If I can pass a function to a function, my function is higher order. And if that function returns a function, it is higher order. So our generate student function, which I just wrote, generate student, is a higher order function because it returns a function, right? So if it takes a function or if it returns a function, it's a higher order. If it does not take a function and does not return a function, then it's not. If it has functions inside, yeah, that's kind of a gray area, right? So we may consider them higher order, but normally people would consider them normal functions. You're just using the kind of internal functions here to structure your logic. But if the function takes a function, or if it returns a function, or both, then it's definitely higher order, right? So remember that. So a function that takes one or more functions and produces. Yeah, that's a very good definition. Perfect. So next. All right, iterators and functional style. So here we take, we're trying to calculate a sum of squared of odd numbers. So we have a list here, and we try to calculate a sum of squaring the odd numbers from this thing, right? From that sequence. So we're doing a map. And then here we have a lambda, or f, as they call them in Rust, closures. It's an anonymous function. Is this function a closure or not? Is this function capturing something from the outside environment? No, it doesn't, because you pass it a parameter, and that's the only thing that function is using. It's using the parameter, right? It's not getting anything extra from outside. So if you passed n to it, it calculates the square of n. So this is an anonymous function which takes one argument and produces a square. It's not a closure, but in Rust, they would call it a closure, right? Instead of calling it anonymous function or lambda. And then we have another one, and another one takes a reference to that return of the mapping, right? Was the mapping by reference or was the mapping by value? By value. Here we doing by reference. Why would we do by reference? So with the map, so here we have a list of numbers, right? And then we taking one number and what we are doing with the map. So we have a list of numbers, and then what happens? We taking those numbers and we squaring them, right? So we have a new list of numbers, right? So it does not make sense to do anything by reference because we have to get the second list by value. We have to get the second list of values here, right? So then what we do here? We saying limit this list only to the values which are less than the upper limit. We have some upper limit, and we kind of take while those values are smaller than the upper limit, right? So we want to do it in place. We don't want to make any copies. We don't want to make anything by value. We want to kind of just take from this list up to the certain limit. That's why we're doing it by reference, right? And the same with the filter. So then on that list, we also filter the ones which are odd. So if the number is odd, we leave it. But otherwise, we throw the numbers out. So we kind of trying to do it in place without making additional copies. And then we are doing a fold. So look at the fold. So the fold just sums everything up, right? So it's the final operation. So we generated like from 0 to infinity. Oh, yay, we have infinities. Like we have a collection which goes from 0 to infinity, right? Can you do this in C++? No, you can't. Can you do it in Golang? No, you can't. You can do it in Rust, right? Can you do it in Haskell? Sure, you can, right? Because of lazy processing, right? So here in Rust, you can also do it. You can say, I have numbers from 0 to infinity. Deal with it, right? And then take all the squares of them, take up to the upper limit, and then filter the odd ones. And here what we have left, we sum. We say, yep, just sum all those numbers. And you see, again, we are not using it by reference. We're using it by value because we create a final result. We kind of, again, we're not doing something in place. We kind of calculating the final result, right? So we're calculating the sum. Is this code kind of clear now? Very similar to Haskell, right? In Haskell, you do the same thing. The syntax would be different, but the processing would be exactly the same, right? So now pay attention to this fold. Okay. Is it a left fold or right fold? Okay, and that's the question. The question is it a left or right fold? So you can guess. If you don't know, you should say you don't know. I'm not sure if I don't know is pointed though. If you get points for I don't know. Okay, so why it is a left fold? So who knows who voted that it's a left fold and can explain why it is a left fold? What do you think? So how do we recognize left fold from a right fold in Haskell? What's the easiest like rule of thumb? So the easiest rule of thumb is because we have the accumulator and we have the values from our collection, right? So when we are folding it, we have something to accumulate into, and we have the values being passed as arguments to our accumulation function, right? So the right fold has the accumulator on the right-hand side and the values coming to the left-hand side of our function. And the left fold is the opposite. It has the accumulator on the left side and the values are coming to the right side, right? And here you have the left and right arguments and the accumulator is on the left. So you could kind of make a informed guess that this fold will be a left fold, right? And they probably should name it L, fold L, just to make it clear. But it is a left fold and the accumulator is on the left-hand side. Folds are also on the exam. So if you haven't studied folds yet, then you kind of need to study the folds a little bit, at least. All right, so that was a hard one. And Tim is the winner. Congratulations. So enumerations. As I said, enumerations are very powerful in Rust, and they are very similar to type system in Haskell. So if you familiarize yourself with Haskell type system, then enumerations in Rust will be very familiar to you. They are very similar to algebraic data types, and option and result are the two most famous examples, which are the same as maybe and either, and they are heavily used in Rust, right? So if you used maybe and either, then you will say, oh yeah, it's the same. It's just more pain in the ass to use it because you have to use those methods and you have to remember the syntax. With maybe and either, it's kind of like, it's like everything else. So you don't have to remember anything special. So then the enum is like, remember in Haskell, you can say data, and then you kind of define like with the bar, you define the instances, right? So it's the same here. You say a web event can be page load, can be page unload, and then you have the extra parameters to the things that you defining. So like a tuple, for example, with a car, paste with a string, or you can even have a struct, named struct inside your type, right? It's exactly the same as in Haskell, right? The syntax is different, but the concept is exactly the same. So then my favorite like whining about Rust is the loops. So in Golang, they sort of, the designers of the language, they thought, and they said, yeah, let's simplify all this nonsense about the loops and just have one keyword, right? So in Golang, you just have for. And then if you don't say anything, it's like an infinite for, like you loops infinitely. You can say for something to something, or if you say for a condition, then you're doing until the condition is fine. So it fulfills all the possible use cases and they just have one keyword, right? In Rust, they have three, right? And then you have to learn like that this one is for infinite loops, this one is for some types of loops, and this one is for the condition, right? So they make it so powerful that, you know, you have a keyword for every possible loops, right? And then you want to do something. So while C, you want to do stuff, but you want to do stuff like one time without checking the condition, right? So if the condition is false, you still want to do stuff once, right? So what do you do? Like what do you do in C? In C, you do like, of course, in Rust, you can do this, but that's like which principle it violates. Don't repeat yourself, right? Like right now you see, come on, Mariusz is just like one extra like do stuff function call, right? But imagine that this do stuff is like 30 lines of code, which you have inside those brackets, right? You have to copy and paste it before you have your while, right? It's ugly like hell, and you kind of copy and pasting your code, right? So it's very like, it's a symptom of a very smelly code, right? So you don't want to do that. So in C, you can do this, right? You can say do stuff while condition, right? You have this reverse while where you don't check the condition yet. You do stuff first, and then you check the condition. If it's true, you go back and you do it again, right? So you have this nice structure, but you don't have that in Rust, right? So what do you do in Rust? You either do this with the empty block, or you have to do this with this if statement, right? So it's ugly like hell, even though you have 3 keywords, right? So why? Why do you need 3 keywords where you still need to do this kind of ugly things if you have to do this particular case, right? This is ugly, but it's less ugly than doing this, right? Like this is more ugly than than those two things, right? All right, so I will stop here. We have some practical exercises to go through, but I will stop here with the lecture and I will go back to the quiz and we will go over some quiz tasks instead. So I will stop recording.